So today we will be focusing more on the data part of it. But before I jump onto the data, we want to be very clear with the concepts, with the more detailed concepts of the algos that we will be using and etc. And I think last class we discussed how we will be training our data on the predefined data set that we have with ourselves, and then probably test it on the newer data set that we will get. Right now, and we have also decided that the problem statement that we are going ahead with is kind of classification, because we have a data set with us where we have labels. We have the labels, and we just need to determine if that person can get, or if the person can basically get diabetes or not. So it's like an classification problem statement where we are basically labeling it as 0 as and 1, right? So that is what we are basically conceptually focusing more on. So I'll just reshare my screen. Give me a minute. Cool. So I just want to give an overview of all the data, or the steps that we are going to follow, etc., all of it, right? Okay, so Parna is asking clustering. Okay, like I mentioned, that if our data set would have been something where we don't have a label, yeah, we could have clustered it. But right now, I was mentioning, like in the last class, that we are going on with an open source data set wherein we have the labels. We have the labels, and we are considering it to be a superset data, basically our EHR data, or electronic health record data, where we have a lot of information of with different medical conditions, whether a person has gotten diabetes or not, type 1 diabetes or not. So that makes our job much more easier by just choosing the algorithm as classification. Right. So the very first thing that I want everyone to be clear with is the steps that we basically are going to follow. So we have, very basic steps. We need to just have a quick look at the data. We need to clean up the data, explore the data, do our hypothesis testing, and lastly, build a model. So looks very simple, right? Looks very simple to everyone. Doable, right? It's doable. Because see, at the end of the day, it's our project, right? It's not me giving you the answers right here, but it's us working on the same project. So you guys need to, at the end of the day, complete the project on your own as well, right? So you need to be equally onboarded on the project like I am. So let me know your views at every point of time in the chat section, and let's make it super interactive as well. Cool. I got a lot of yes, so everyone is onboarded with me is what I assume. Quick overview of different type of machine learning algorithms for everyone who is new to this, and kind of a division to people who are not not new to this, who have been going through the same topics. So we in machine learning, we have kind of three major types: supervised learning, unsupervised learning, and other types of learning. So supervised is basically when we have a set of input to a target variable, or our data is kind of labeled. Like for example, if we are predicting stock prices, right? Something that we are predicting in terms of continuous values, and it is a kind of a value which we are being able to exactly label our data with. Same way with classification, where we have a label, whether a person will get diabetes or not, whether a person will pass the exam or not, whether it will rain today or not. So we have different target variables to predict too. So that is basically having labels, and that's basically called supervised learning, right? Nothing documentary, no objective to predict type, and that's the main objective, right? Just a question over here. The document, no objective is to predict type 1, right? That's the main objective. Yeah, the main objective over here is how many people are likely probably have high probability to get type 1 diabetes. And for that, we basically, like we discussed in the last class, we have to build a model which knows how to predict or give us the probability of whether a person will get type 1 diabetes or not. So we are focusing our main focus on right now on that part where we can perfectly build a model which can do our job, right? So everyone is clear with this part, which is what is our objective and how we are heading towards it.
Yeah, yes.
Can you repeat it, Meghna, once again?
Okay, our objective is basically to identify people who have high probability of getting type 1 diabetes so that we can exclude them from the clinical trials. We have already discussed why we need to exclude and everything out of it. But to get that probability or understand out of these people in our clinical trials, let's say 500 people who are actually probable to get type 1 diabetes. For that to happen, we need to have a automated system or like a model which will tell me a yes or no. For me to get that model up, I need to build the model, right? I need to train the model. So right now our focus is to train a perfect model which with a higher accuracy can predict or give me the probability of whether a person will get diabetes or not. So that is our main focus on, and that's why we are focusing so much on the learning technique and the different type of learnings that we can go ahead with. Clear?
See, here labels means different type of things on like BMY. That's why we are calling labels, right?
No, your label is basically your target variable. You're labeling the data that for this BMI, this age, or this insulin, or this medical conditions, the person is labeled as 0. Maybe 0, which means the person didn't get diabetes. Maybe if it is 1, labeled as 1, that means the person got diabetes. So your target variable is basically your label.
Okay, we'll call the target variable as label.
Yes. Yes.
Okay.
Clear?
Here we can the target variable is like how can we identify the target variable actually?
Usually it is always given in your dataset, but in real world, when you don't have that, you still have an overview of which do you want to visualize as target variable. So that is something which, again, more you understand the data, more you get through the problem statement, you'll understand. So let's say, let's just jump on an example. Let's say you have a retail store data on a customer level, okay, and you're trying to understand that for the next campaign that I'm sending, next marketing campaign that I'm sending, who have higher probability to buy the product. Now you have I'll tell you, you have the data set of customer details. So you have the customer's ID, you have the customer's sales details, browse details, customer's demographic, basically age, income, region of residing, or how frequently he buys, what is the maximum amount and minimum amount of sales that he makes, and whether in the last 6 months, whether in the last 6 months he bought with us or not. Now what do you think will be the target variable over here if you're trying to predict whether the person will buy with me or not in the future, just to tailor the marketing campaign better?
Yeah, I think we can select the customer sales by based on that we can see that whether he is going to buy or not.
Exactly. You will look at the customer sales and see that whether in the past he has bought with me or not. And that will be kind of your target variable, because that will help you predict that what will happen in the future, right?
Whether he's going to get profit with us or loss with us by based on that one we can able to know it.
Yeah. But you got my point, right? How to basically choose the target variable.
Yeah, I understood.
Okay. Everyone clear till here? In terms of categorical variable, right? Yeah. Okay, great. So we discussed about supervised learning. We got to know about different type of learnings like classification, regression, and then we have our unsupervised learning where we don't have any particular label or target variables with us. Therein we basically segment or group our customers. We call it clustering or segmentation, wherein we don't have a label. So we kind of group similar data points and then give them label according to our needs. So there's no predefined label over there. So that is unsupervised learning. There are other type of learnings like reinforcement learning, etc. So can anyone give me a good idea of what reinforcement learning is? Anyone, any rough guess, anything that you think about?
There will be an agent, and depending upon the environment, like it will be automatically learning things of its own on the own. Is it so?
Okay. 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 What about others?
And also, a penalty will be given if it is right, and if it is wrong, there will
If
be.
it is
I'm
wrong,
sorry, if it
penalty
is
will be given.
yeah,
If
yeah,
it's
if it is
wrong.
wrong, penalty will be. If it is right, some awards will be given.
Okay. Okay. Any more answers?
What about image segmentation?
Okay. Are you like asking me or answering
No,
about
no,
reinforcement?
no. I'm saying that only. Image segmentation, like like depending on all the different segments which are present, we continuously check whether that's the correct one or not.
Okay, so image segmentation, I mean, you basically mean that you're basically converting an image into different regions and then
Yeah,
understanding the label out of it, right?
yeah.
Huh, yeah, okay.
It is
So,
reward type of
sorry?
reward type of.
Yeah, okay, okay.
Basically, the algorithm behind the chat GPT, right? Like what would be the next prompt word, probable word coming out? I think that is
Hmm.
reinforced.
Yeah,
And it also follows trial and error method. So based on that, it will give the best suggestions.
okay. Okay, so I got quite a few answers which were on point. So reinforcement learning is exactly, let's in very layman terms, let's think of it as a human mind wherein we make decisions every day, right? So let's say today you are going to office or your college and you take a way, and then you measure the time it took you to travel to the destination. So based on that you make a decision that tomorrow should I take the same path or should I try some new path. Maybe if it took you too much time and it actually resulted you in a loss at the destination, maybe you reached after the meeting time that was given to you, that is a loss, right? So if something like that happens in your mind, you know that okay, this is something I'll avoid tomorrow I'll take a better path or something like that. Reinforcement learning exactly works like that, where there is an agent and there's an environment where the agent basically takes decision and clears a path where it knows that in which path there is better outcome and which is achievable. And the best part about it is that it is a self-learning algorithm, right? So yeah, so all your answers were actually on point. So yeah, great. Cool. Let's start with the model building. So for model building, as we all know that there are multiple parts to it, but at the end of the day, we need to know what we are solving. So once we are clear with our problem, once we are clear with our goal, we basically start training our data. And for that, we need to first prepare our data set, because most of the data that we use are not pre-processed, right? Some may be having categorical variables, and most of the pre-processed libraries or sklearn that we use, they don't allow a categorical variable, or they don't process categorical variable. So therein we maybe need to convert from categorical variable to numerical variable using encodings, etc. Or maybe in your data there is a lot of missing value, which again a lot of algorithms don't process with. Then you go back, you do some kind of treatment on the missing values. You want your model to learn from better set of data and not from noise, so you do something about the outliers, etc. These are all part of preparing the data set or pre-processing the data. Once we are done with that, that's when we start building our model. Once a model is built, we evaluate it and then we interpret the model results. Now, a lot of the cases I've seen that people stop at this state. They basically test the model on the testing part and it's done. That's it, it's done. Maybe they got the accuracy classification report, or let's say the regression score, etc., and that's done. But that's not the case. A very big part of machine learning is also to understand the model results and interpret the model results. And there are multiple ways to do that. This part of the work is what we call as MLOps also, though MLOps is a vast or a very big domain out of it. But yeah, interpreting model results is again very important. What is model understanding out of the data that I have given? How did it learn? How well did it learn? What is it trying to predict? Is there some kind of correlation that I am trying to gain from the model results, and all of it? So these are all the steps that are involved in model building, to be precise. And now let's see how we prepare our data sets. So for preparing our data sets, again, it's quite simple. I think most of you guys are aware of what is a dependent variable and an independent variable, right? You guys are aware of independent and dependent variables, right? How many of you guys are familiar with dependent, independent variables? And if you're not, please type in a no. I'll be happy to explain it. Yes, I got all the yes. So everyone is aware of what is independent, dependent variable. And even if someone doesn't know, it's basically our target variable becomes our, dependent variable, and all the other variables or features that we have in a data set using which we are trying to predict that target variable becomes our independent variables. So once we have our dependent and independent variables, we basically divide the whole data set into training and testing part, so that I train my model on a part of the data and then test it out in the other part of the data. And I know that my model is being able to capture unseen data patterns as well. So that's about the steps of preparing the data set for my ML part. And I hope everyone is clear with that, because I think this was pretty known to all you guys and clear to all you guys, right? So just let me know if you guys are clear till this part.
Can you explain this defining the goals and building the model and interpreting the model? What is the interpreting? Like interpreting is like we are taking the input, what is the observations from the model, right? That's the interpretation.
Interpretation is basically interpreting or understanding what is the model doing, or how is it understanding my data. Let's say you built a random forest model, okay, or let's say you built a XGBoost model. You have built it, you got the accuracy, you got the precision, you got all the metrics, but your job is not done. You have to see that whether my model, at the end of the day, you're training the modelers, you have to see that how well did my model understand the patterns of the data. Did it even understand the patterns of the data, or is it capturing the noise in my data, or what were the most important features that my model has used? Is it being able to handle correlation between my features? All of that, which feature is negatively impacting. If we know out of 600 features, 60 of them are of utmost importance, we can build a second level model with just the 60 of those models, 60 of those features, and get a better model out of it, right? So all of this comes as a part of interpreting the model.
Okay, got it. Yeah. Clear.
Okay, great. Now let's move on to the very popular algorithm, which is logistic regression. Whenever we talk about classification, logistic regression is something which always comes up on our mind, because it's a very popular classification algorithm which is almost used in every classification problem statement, and mostly on problem statements where there is a binary outcome. Binary outcome means something which is in the form of true, false, or 0, 1, etc. Yes or no, basically true, false kind of thing. So whenever my target variable is in the form of true, false, yes or no, that's when my logistic regression comes very much handy. So conceptually, logistic regression is basically a statistical method which is basically used for binary classification problems mostly, though you can do multi-level classification as well. But yeah, where the response variable is basically categorical, and it has two classes: yes, no, 0, 1, true, false. And we are basically modeling the probability of any event or any instance belonging to a particular class, and maybe what's the probability of that event occurring based on the number of predictor variables or independent variables that we have. So that is conceptually what is logistic regression. So I hope you guys are clear with here till here. Why is always binary? Logistic regression is known to be very smooth with binary classification, but that doesn't mean it cannot do multi-level classifications as well. It's just popular enough with binary to answer your question.
Binary means yes or no, right?
Yes.
The answer output will be like yes or no, whether
Yes or no, true or false, all of it, 0 or 1, 2 out, all yes or no, like that.
Okay.
One question. Are we going to be using multiple models here in this project, or just
Yeah,
one?
we will use multiple models.
Okay.
Hi, are we actually
Yeah.
going to like find do the projects together?
Sorry, I didn't get your question. Can you please come again?
Are we actually going to do the project together?
How many? Sorry, I'm not getting it.
I said, are we going to do the project together?
Yeah, we are going to do the project together. So you know what, how we'll work out this is that every class that we are having, I'm basically trying to give you guys an idea of what happens in real world and how we are conceptually utilizing a lot of concepts. So last class we understood a lot of healthcare. This class will work on the data and the modeling part of it. And what at the end of the class, I'll tell you what you have to do in this project. And that's how we will be growing. So at the end of the day, though I am explaining you a lot of it, but I expect you to also continue with the project when we are done with the class. So that's how you will also be working on the project.
I thought we were going to do the project together to see real time, to actually see how you do it and how you put us through. Then we can do other projects ourselves also.
So you're basically saying that how you the data part and how does it look, all of that.
The model building of this.
Yeah, we'll do all of it. Yeah, we'll
Okay.
do all of those implementations. It's not going to be all theoretical for sure. This is just me giving a brief or a complete understanding of the models and machine learning, because some of you may know about the model, some of you may not know, but it's always good to know in and out of the maths of the concepts behind the models that you will be using, so that you know what you're doing, and you will be able to basically explain your projects to the best when you are explaining it to your interviewers. Cool. So conceptually everyone is clear with binary logistic regression, right? Like what it is and etc. I think we are talking a lot about binary logistic regression, but it's because we have two outcomes, 0 1, yes, no, etc. But we can have multiple labels also. We can call it multi-level or multi-label. So can anyone tell me what's the difference between multi-level classification and multi-label classification? Can anyone tell me that? What I'll type in the chat box as well. Multi-level versus multi-level. How many of you guys know the difference between multi-level classification and multi-label? I'm sure you guys have learned about logistic regression. Maybe most of you have learned about logistic regression in the back end, and that's why I want to talk about a lot of stuff. But yeah, I just want to know what's your idea about multi-level versus multi-label. Any rough guess, anything that comes up to your mind, when you hear the word multi-level versus multi-label?
Multi-label we know, but I'm not sure about multi-level. Yeah.
That's okay. You can explain any one of it as well, which you
Yeah,
think.
multiple label is nothing but when the target variable is having the more than two, we can say it as a multi-level. Yeah, multi-label, sorry.
So you're saying more than two labels or more than two classes.
Yeah, more than two classes in a target
Okay.
variable is going
Okay.
to be multi-label. Yeah.
What about others? Then Lakshmi says
Hmm.
no idea. Okay.
I think multi-level means like we have more than two categories to predict,
Okay.
and multi-label would be like we have two target variables.
Okay. But isn't it the same thing then?
Yeah, multi-level is basically that's what I think. I'm not sure. Maybe it's the target variable will be dependent on the target variable of some other.
Yeah.
It's like a inheritance.
The type of data are grouped in different levels.
Okay. Okay. Okay.
Yeah.
Okay, what else? What else is coming on you? Try to decode the word. Even if you don't know, it's fine. I don't expect you guys to know everything, right? But I want you guys to think about it. What do you incur from the term multi-level or multi-label?
Multi-level, according to I decode like that same thing is happening maybe in different type of levels. They are something grouped in different levels.
Something grouped in different labels, like for example, gender.
Yeah,
It can be male, female, or unknown, like
yeah,
that.
yes.
Okay. Okay. And what about the other one?
Multi-label.
Yeah.
Same type of classifications for one things which are using 1 or 0. For that we will label as like different things. I can decode it like multi-label.
Okay. Okay.
For
Got it.
for both the outputs we will use like 1 or 0, but with different labels. So I am treating that as like multi-label.
Okay. Okay.
I think multi-level is hierarchical concept where we label by levels, and multi-label is more than one category, I think.
Okay. Okay. Even in
I
the
think
chat we have
last like multi-level should be that CNN, right? Like there are different levels basically that network, right? That I'm forgetting the name, neural networks. So that's multi-level.
Okay. Neural network is basically a way to, it's like an algorithm. Let's think of it as like an solving technique or an algorithm, right? What I'm asking you is basically a concept, like what is multi-level or multi-label. It's not any algorithm, it's just a concept. Like how we have binary classification, same way. We do have some answers in the chat box as well. The task is to classify between more than two classes. That's multi-level. Okay. Multi-level can have multiple outputs. Multi-level can have only one target. Okay. Any more answers or any more guesses? Okay, cool. So let me help you guys with this. So multi-level. Okay, multi-level classification. The term itself says that there is multiple levels inside it, right? So it's also called as multi-class classification. It's basically a classification problem itself, where there are more than two classes or categories that the model needs to predict. In multi-level classification, every instance, every row is assigned to only one and only one class out of the possible classes. Let's say there are three possible classes A, B, C. So every row will either have A or B or C. It cannot have A, B both, or it cannot have A, C both. It can either be A or B or C. So the goal is to basically categorize all the data points into distinct and mutually exclusive groups. So the term that you are always going to use with multi-level is classifying into mutually exclusive groups. What does mutually exclusive groups mean? Two groups which have nothing common in them. That is multi-level. Okay. I'll tell you guys in detail. Okay. But let's understand the concept first. Okay. The characteristics of multi-level classification is basically where each data point belongs to exactly one class, and the classes are very mutually exclusive from each other. Okay. Mutually exclusive in the sense a person can either be female or male or unknown, right? So there again, here again, the example is not exactly mutually exclusive. Let's think of a better example.
I think like tossing a coin and then a dice.
A dice is a better example. Tossing a coin will basically be again binary,
Yeah,
heads or tails.
both of
Yeah.
them together. Sorry.
Yeah. So it's more like either you can get one, or you'll get two, or you'll get three, or four, or five, or six. You cannot get one and two both, right? It's just rolling one dice at a time. You can get any one of the outcome. So like let's say we are predicting the type of the fruit. It can either be an apple or a banana or an orange, right? Based on the features, like let's say the color is red, so it most probably will be a red. I mean the apple. So based on different features like color, shape, size, all of these things that we are trying to use and predict the type of fruit. So the fruit can be either an apple or a banana. Fruit cannot be both apple and banana, and apple and banana are completely exclusive from each other. They cannot have any similar thing in them, right? So that is multi-level. Multi-label, on the other hand, is a classification problem where every instance belongs to multiple classes simultaneously. It's not like multi-level classification where every instance was belonging to one class. Here in multi-label classification, every instance can be associated with multiple labels or categories. So again, the key characteristics is that every instance or every row can be associated with one or more classes, and the classes are not mutually exclusive with each other, right? So all the classifier chains or the a lot of algorithms are there which are basically segregating or categorizing my data into multiple classes, which can have one data point, or one particular row can have two or three classes together as tagged with them, right? So let's say for example, problem statements where you are basically tagging a document with multiple labels, right? Let's say there's a document, it has stuff about technology. Let's say you're working with NLP, natural language processing, okay, where your job is basically as you are being given tons and tons of document, and you basically have to devise an algorithm to basically read all the documents and give a subject to it. Like let's say you have to say that whether this document is about technology or science or history or whatever it is. Now a document can have multiple labels, right? It can be both about technology and science and maybe health, like the problem that we are solving over here. It has machine learning, it has healthcare, so it has two things over here, right? So based on its content, it can have multiple labels in it. So that is like one of the basic examples of multi-label classification, right? So if I summarize, multi-level is basically where the classes are mutually exclusive to each other, and that's the term that you're going to use from now on whenever someone is asking you what is a multi-level versus multi-label. Multi-level is when you assign only one class to each instance, and the classes are mutually exclusive. Multi-label is when you can assign more than one class to every instance, and that those classes are basically not mutually exclusive. And you have a lot of algorithmic approaches for each one of them. NLPs or a lot of classifier chains are basically being used for multi-label classification, but multi-level, as we all know, very common, and the one that we are still trying to do. A person has diabetes or doesn't have diabetes, right? So we can use logistic regression, decision trees, SVMs, random forest, all of it, right? So this was the difference between multi-level and multi-label, right? One more example of multi-level can be if you're trying to predict a genre of the movie, right? So the movie can be a comedy movie or a drama movie or an action movie. That can be multi-level, right? Multi-label can be assigning tags to, again, the documents or blog posts based on their content. Let's say you have a Instagram reel that you saw, and you want to assign a label to those reels based on their content. Now a reel can be about food and maybe about some social message or something like that. So it can be both, right? So that's like an example of multi-level, right? So it's very important to understand the difference between multi-level and multi-level, and that's why I wanted you guys to give it a try. But yeah, that's the difference between multi-level and multi-level. So are you guys clear with what's the difference now?
So one question regarding it could be vice versa, right? Because one row could be in multi-level, you have say, right, not mutually exclusive. But in the case of multi-level, we have or have not, right? Mutually exclusive.
No. So in multi-level, it's like, for example, what you're doing right now, you're predicting diabetes. So either a person will have diabetes or not have diabetes, right? Nothing in between. And in the second case, when you're tagging a document, the document can be about science, can be about technology, can be about healthcare. So it can be all three of them. So that's the difference between multi-level and multi-label. In multi-label, you can assign that particular instance or data point to multiple classes. But in multi-level, which was the first one that I was talking about, you cannot assign multiple classes to one instance. It can only be one label. That's it.
So, okay, in multi-level means when we're talking about whether having diabetes or not having diabetes, we have to stick only to that part only.
Yes, yes, yes.
Okay.
I think the question is in multi-label, can any instance be of only one category? I mean, like
No, no.
it has to be belonging to two
I
categories.
mean, if it is like, yeah, either any one of the row that is having just one category and it is not, let's say, one document which is entirely and purely technology and it doesn't fall under science or health or anything else, that's okay. But overall, if we see, maybe out of 10 rows, 8 of them had their label with 2 or 3 labels in them. So that's a multi-label classification, if that answers your question.
Yeah, but some exception might be there, like maybe one.
Yes. Yeah. But in the other way around, multi-level won't have ever
Yeah,
any
I got
exception.
you.
Yeah.
Hi, can you
Yeah.
please give examples with this diabetes something when explaining this
Yeah.
multi-level
Yeah. So
multi-level?
the diabetes thing that we are trying to predict, what are we trying to predict? We are trying to predict whether, even if we think of it in a very simple, very layman term, we are trying to do what? Like, let's say we have 100 people with us in the clinical trial. Now, out of those 100 people, how many of them will have diabetes, right? We're predicting whether that person will have diabetes or not, right? So either that person will have diabetes or that person won't have diabetes. Now you may question me saying that what about the people who have preconditions or pre-symptoms but they have not been they didn't enter the diabetic zone yet? So again, that will be labeled as doesn't have diabetes, right? So there's nothing in between. You either are diagnosed with diabetes or you're not diagnosed with diabetes. So it becomes a multi-level problem and not a multi-label problem. To answer your question.
Okay, so that means a multi-label.
So multi-label can be, let's say, in terms of healthcare, a person, you're trying to see that with all the medical conditions, whether a person can have maybe a person can have both high blood pressure and high diabetes level. That's possible, right? A person can have high blood pressure and high diabetes, or a person can be cancerous and that person can have high blood pressure. So you can have multiple diseases in you. But multi-level, on the other hand, is that you either have high blood pressure or you have low blood pressure or you don't have blood pressure. So there's nothing other than that, right? So that's the difference, if that helps you.
Okay.
Right?
Thank you.
Here one
Yeah.
doubt. In
Yeah.
multiple level means, okay, you said that like only predicting diabetes or not having diabetes. We can't involve any other activities like, you just mentioned like high blood pressure like that. So again, it will be called as like multiple label or multi-level.
It's called multi-level. Now, if your problem statement entirely is just like in our case, right, what we are solving, it is entirely in understanding what's the probability that the person has diabetes. Basically, if a person has diabetes or not, let's simplify it. It's a classification problem statement. Either the person will have diabetes or the person won't have diabetes. So it's clearly a multi-level because the groups are mutually exclusive and a person can either have any one of it, either diabetes or not diabetes.
No, here I'm asking like that. Oh, we want to include the blood pressure also, whether the patient is having.
Yeah. If you include it, it becomes a multi-label, right? But in our case, we won't include it because our whole study, our whole objective is only to study diabetes over here.
That's what I'm asking.
Yeah. Yeah.
Got it.
Got it?
Yeah. Only single thing we will take it as like multiple level.
Yeah.
Okay.
But in case of binary, I mean, that's what the difference between binary and multi, right? So binary, we used to have two variable out of which, like, we can say yes or no, like whether a person may be diabetic or non-diabetic. Only two probabilities there, right?
Yeah.
So we used to call it binary, right?
Yeah,
If
it is binary.
Yeah. Then if we're talking about multiple and we are saying the same thing, like if a
I was
person
trying to give you an example on it, like Definitely, I get your point. You're saying that if a person has diabetes or not diabetes, it becomes a binary problem because there are just two classes. I'm saying when the same thing happens with three classes, but only one class or one label is assigned to each data point, it becomes multi-level. But I was trying to build on the same diabetes example. So don't confuse yourself on that.
Okay, multiple. I mean, it will be like if I'm talking about binary, it will be more than two, right? In case of multi-level, right?
Yeah,
LEVL.
multi-level, multi-label, both will basically have when there is more classes, right? So multi-level is basically when there are more than two classes. Multi-label may you can have more than one classes and still one data point can have more than one classes assigned to it.
Yeah, common will be there in case of multi-label, right?
Yeah.
Thanks.
So Meghna, how can we solve this multi-label problem? So
Yeah, there are multiple algorithms to that. It's kind of complex. If you talk about NLP models, that's one way of doing it. There are classifier chains. That's one way of doing it. There are relevance methods. There are label parset methods, which are kind of complex. Neural networks that helps us do all this job. So what we are learning now is a multi-level problem statement or a binary problem statement, which involves our supervised learning methods, like your logistic regression, XGBoost, random forest, all of it.
Okay.
Yeah. Cool. So is everyone clear with multi-label versus multi-level? Are we clear on this part?
Yeah, yes.
Okay, just give me a minute. I'll grab some water. Just a minute. Cool. Yeah. So again, coming back to our topic, we're talking about logistic regression, and now we know that how we are predicting a binary problem statement, how we are predicting whatever we are predicting is kind of a binary response. Everything is based on the response, right? So given a bound binary outcome variable, let's say y, that's our outcome variable, right? Yes or no, or 0 or 1. So we have multiple predictors over here. We have multiple predictors, let's say age, whatever we discussed in the last class as well. Age, smoking habits, insulin levels, BMIs, etc., etc. So those, all of that becomes our predictor variables or our independent variables, like which we are basically seeing in the form of x1, x2, etc. Right? So logistic regression basically involves two parts to it. But before that, before I discuss logistic regression, I want to know how many of you guys are clear with logistic regression. How many of you guys know about logistic regression and the maths behind it? Shruti says me. Deepika says me. What about others? If anyone doesn't know, please let me know. Please say no if you don't know about logistic regression. That is completely fine. But I just want to know that if you guys know about logistic regression or not. Any more
We
response? Yeah.
do, but just the theory part.
Sorry?
We do, but not most of it. Like
Okay.
just basically the theory
Okay.
part, and we don't really know the coding. Me, I'm speaking for myself.
Okay. Okay. Got
Yeah.
it. So I'm assuming most of you know about logistic regression, and most of you know I'll definitely give a recap about it, an overview about it. I definitely know that most of you would know about logistic regression. It's a very popular algorithm, and the moment you start learning classification, I think this will be probably the first algorithm that you will learn about. But there are a lot of in and outs about logistic regression which maybe you won't be aware of, right? And it's good to even have a recap and an overview of it, right? And that's the whole point of when we are doing the project. It's better we encapsulate a lot of information within us, right? So my question to all of you guys is, we all know that we are trying to do classification, but we are using logistic regression. So why do you think the algorithm is named logistic regression when we are actually doing classification? I'm sure a lot of you will know the answers, but yeah, let me know in the chat box.
The output of linear regression will be used as an input
To
our logistic model.
and what happens with that? What happens with the output of the regression model?
Let me recall.
Classify basically.
Classify how? Like I want to know it in a bit detail.
In a probability.
Okay, let's say I got a score of, or let's say I got a regression value of 9,000. So how do I know that? What's the probability?
It's by sigmoid function, like we find the
Yeah.
probability, and on finding the logs of the sigmoid function and finding the log of odds of it, it becomes a binary equation. I mean, like a logistic equation. That is why, like we say, the logistic to be following the linear trend. Yeah, I mean the linear equation.
Okay.
It's linearly related to ln of odds ratio.
Sigmoid function act as an activation function to convert the range from 0 to 1, and yeah.
Okay. And let's say it got converted to 0 to 1. Now every value that I have is between 0 to 1.
Yeah.
Now how do I know that who has diabetes or who doesn't have diabetes?
With the threshold value, we can actually find that.
Okay.
We need to.
Okay, got it.
It's a hard margin. No, it's not a hard margin. Sorry, it's a soft
We use
margin,
this
right? Yeah.
maximum likelihood.
Yeah. Sorry?
Maximum likelihood. We use this maximum likelihood method to do this.
Okay.
We can find the optimum threshold using the Uden index, like or else with the cost method also, and
Okay.
we can find the threshold value, and we can actually predict the values. Yes.
Okay. But okay, got your point. Absolutely got your point. But the whole point is that it's termed, regression because it is regressing and then it is classifying, right? Everyone agrees to that? Yes. Can I get some more yes? Can I get some more response?
Can you repeat it again? Sorry, I didn't get it.
I'm asking you guys that, the whole point of saying it is as a regression, naming it as logistic regression is because we regress and then we classify.
Okay.
Can you explain what regress means? Like, I mean, like when you're saying
Basically, we are getting a continuous value out of it. Let's say any continuous value, we're basically performing a kind of a linear regression, and then out of that value, we are doing the classification.
Okay, sounds
good. Cool. Everyone agrees with me? Cool. Great. So yeah, that's the point. The first part of it involves a part of regression where we have our very basic linear equation, wherein we get for every data point, we get a score. We call it score. It's a basically regression value wherein we have a value which is assigned for every data point. Now, when we have the values, we basically do the classification like how you explain. But let me try to explain you it in a more data point of view. Less of mathematics, but more of data point of view. Okay, you have 10 variables, you have one target variable, so total of 11 feature variables. What your logistic regression basically does is runs through the whole data, assigns relationships between different feature variables, and understands what is the best fit line or what is the best relationship that it can get between the target variable and the predictor variables. And for that, different weights or different coefficients get assigned to each of the variables. Let's say for our diabetes prediction, your insulin has a higher weight than age in predicting diabetes, right? Maybe a person who has higher insulin will have a higher chance of getting a diabetes, but it is not that correlated with age, right? Quite possible, right? Quite possible that age feature gets a higher weight than, insulin feature gets a higher point than age. Yes, you all agree with me? Exactly. So it is basically understanding what is the relationship between the features of my target variable and my independent variables, assigning a relationship, understanding the weights. It's basically understanding what weights can be assigned to different features within our data set. And then with the help of those weights, it is basically regressing and assigning a continuous value within for every data point. For every row, it basically has a regressed value or a continuous value or a y value which it got for that data point. Now that value can be anything. It can be minus 9,000, it can be 9,000, it can be 200, it can be 800, it can be absolutely any value. Now when I got a score of such varied range, when I don't know what I'm going to do with that, right? I don't know whether this person will be be having diabetes or not, but just by knowing the regression score, right? So therein comes the advantage or the basic point of using logistic regression, and the term called logistic because it contains natural logarithm in it. So it's basically using the logit function or the sigmoid function. How does it look like? It looks something like this, right? Wherein we basically, just give me a moment. Yeah, so wherein we basically are using our regressed value in the same equation and scaling everything down to 0 and 1. We are basically trying to, basically, let's say it's just like a machine wherein you're giving the whole scores or the whole regression values that we just got out of our model. We are feeding it inside the machine, and it is basically giving me everything scaled between 0 and 1. This is like a very, very basic layman explanation of that logit function, right? So the logistic function of 1 divided by 1 plus e to the power minus z basically transforms all those linear combination of your predictor variables between 0 and 1, and the 0 and 1 is basically your probability of whether a person will be getting diabetes or not. So the goal for us here is to estimate our linear coefficients. That one that we had prior to this in a linear equation, the goal is to estimate the linear coefficients that maximize the probability or the likelihood of observing the outcomes in our, whatever outcomes we have in our training data. And once we have that, we can basically decide on the threshold. Now again, threshold by default in most of the times we use 0.5, but that is not always the case. It depends on the scenario. Sometimes we go down to 0.2, sometimes we go up to 0.6. It completely depends on the use case, and it completely depends on what our data is like, what is the basic problem that we are solving, and all of it. Yeah, so that is basically hows and whats of logistic regression. So is logistic regression now more clear to everyone?
Yes, can you repeat the one second? I missed out.
Yeah, can you please say, for example, age, or say for example, our target variable is they have diabetes or not diabetes, right? And now we have the 10 input variables. The example that you took, age or insulin levels or BMI. So can you assign a value to age and BMI and give us an example, like by assigning the values and then like calculating this for just for the better understanding.
Okay, now let's say your insulin got more weight than age. Let's say right now we just have two variables. Okay, let's make it simple. Our insulin has more weight than age, so naturally your coefficients will differentiate over there. Maybe your beta coefficient for age for insulin will be higher than age, indicating that there is higher resemblance of diabetes with insulin rather than age. And likewise your score will be assigned to each data point. So let's say we have a data point where there is a person with high insulin and maybe age is something which is on the younger side. So that person maybe will be given a score which basically would mean that the person having diabetes is higher. Probability, now what's the probability? Now to get the probability, we are basically using the logit function, which is again scaling it down to 0 and 1. So the whole coefficient part and the weight assigning part has nothing to do with the logit function. It's two part to it. First part, where we assign a linear equation, we understand which feature is giving more importance to our prediction value, which is the best relationship that we can get between our independent and dependent variables. That's how we get the scores. That's how we get the continuous values for each of the instances that we have in our data. And based on those values that we call as scores, we are feeding it into the logit function, which is basically scaling it between 0 and 1. And then again, by choosing the threshold, we are basically trying to understand that which is the best threshold that we can go to classify our diabetic and non-diabetic patients.
So on what factors do we decide that insulin is a more important variable as compared to age when it comes to prediction about diabetes? That I got it, that insulin is definitely is what do you call is a better judge when we say that it is diabetes or non-diabetes. Age is also a good parameter, but at a lower scale, right? So
So
who decides? How
we don't decide that. We won't decide. That is model learning from the data. Model reiterating on the data and understanding what's the best fit relationship. So you guys have when you guys must have studied about linear regression, you must have known how we use a best fit line for our data, right? So depending on the values that you have in your data, your x and y variable, you use a best fit line. Basically y equals to mx plus c. So what will be the values of your intercept and slope to understand the best relationship that you can get between x and y? That's the whole point. The model basically gets reiterated and it runs over and over again on the data to understand the relationship between your insulin versus target variable, age versus target variable, and then assigns the coefficients likewise.
So based on the coefficients, we are deciding which is the more important variable.
Yeah.
And that coefficient is the y is equal to mx plus c means the m part. M is the coefficient we are seeing here.
Your slope, yes.
Slope is the coefficient.
Yeah, but think of it as multiple variables. So let's say beta 0 plus beta 1 x1, beta 2 x2. So beta 1, beta 2s, all of these are your coefficients that are being assigned to all of the features that you have, all of the predictor variables that you have.
Okay.
But in general, like we consider the most significant ones, right, Meghna?
Yeah, we do, but that comes from the part of interpreting the model. The first part is you just build the model, right? That's the simplest part. You build the model, whatever model learns from the data, we utilize the data and we are done. Then there comes the part of interpreting the model, understanding which features did my model understand as the most important ones. And then you can build more on it. You can then be like, okay, if there are, let's say 100 features, out of which 10 are absolutely of no use, they're not even contributing to my predictions, and I got to know it by interpreting the model performance, then you can just maybe eliminate those features and build your model on the rest 90 features again. So you'll get a better or a more robust model. But it is, again, the whole modeling approach is a very iterative method. So it never goes with one iteration, but you do multiple things to get the best model results.
Yeah, I'm not denying that. Okay.
Yeah, and what it denotes is graph. What this graph represent?
The graph that is right now on your screen.
Yeah.
So this is your sigmoid function. This is how it, just look at it like your sine graph. Like basically, if all the values that you have been scaled between 0 and 1. Nothing exceeds 1, nothing, comes below 0. So that's the point.
Okay. So what about the bottom z value?
Sorry?
Z is okay. Coefficient is like
your x can be anything, right? Whatever. Let's say your x is over here, here, somewhere over here, somewhere over here, right? But this is this dashed line. Let's say this is the threshold. So anything above it gets classified as 1. Anything below it gets classified as 0.
0.5. Above 0.5 is
Yeah.
1. Below 0.5 is yeah. Okay.
Yeah. Is the feature selection comes with model iteration or initially, or we can decide? There are two parts of it. We call it feature engineering, where you firstly decide, you can decide that which features am I going to feed into the model. Now, let's say you're working with a customer detail data set, where you are trying to predict whether the customer will purchase with me or not. Now, in such scenarios, there is maybe, let's say there is lot of independent variables. Along with that, we have a variable of customer ID. Will we directly put in customer ID to our model? Will we keep our customer ID column in our data set while training our model? What do you think? No. Okay, what about others? No, right? Exactly. We won't do that, because that column exactly has no value to our prediction. It absolutely has no value to our any of the prediction of the target variable. So that is something we do on our own. We initially decide that this is a kind of processing where we will just discard this feature because it's of no importance. The second part of it can be something where you build the model. Now you understand that out of 100, 10 features are of no use. They're just adding a lot of noise to my model, not even contributing to my model prediction. So why am I going to keep that model in the place? I'm just going to discard it over here, right? So that's the whole agenda. Got it? Great. Okay, any more questions over here? I'll just take a pause.
Just one quick confirmation. So we can build a coefficient matrix to see the correlation between.
Yeah, you can. Yeah. You can see, you can build a correlation matrix and see what's the correlation between the different variables that we have. And it will definitely coincide with a model's understanding of the data as well. Again, model won't learn anything extraordinary, right? Model will exactly learn whatever the data is representing. So it will coincide. But when you build the model initially with all set of features, what we usually do is we basically build our model with initial set of features. Right now, we are using open source data sets, and we are using a lot of sample data sets, right? We don't usually right, for practice, we don't usually work with real corporate data, right? When you work with real corporate data, your data is huge. I'll tell you, there has been, I've worked with data which are like 60 million, 90 million data. Just 60 million, 90 million data that I'm training my model on. And there are features which are ranging from 5,000 to 6,000. Now imagine a model to learn and understand the relationship between 5,000, 6,000 variables. Do you really think all those 5,000, 6,000 variables are relevant to my model?
Not really.
Not, right? And how is it humanly for us to understand out of those 5,000, 6,000 variables just by a correlation? Even if you plot a correlation heat map, you won't be able to visualize it properly. And how will you understand manually which is the best possible features set that I can use for my model? The only way to do it is using a feature selection method. You build a model, you understand how the model is understanding the relationship between my variables, you understand which features are contributing and not contributing, which features are adding noise to my model. You eliminate those features and you build again a model on the only the robust set of features. And now the model will be more robust. Now the model will understand the relationship better, because now the features are all the features that I'm right now building my second model on will be completely contributing to the target variable. So it will make my predictions even more better. That's how we function in real world, just to give you an idea.
But does it not mean like if we have that much of data or variable, then how to pick, I mean, which particular variable is going to give me a correct or good accuracy, right? So
Yeah, the
is it
only
not
way
going to take a
to
lot of time, or it may vary from person to person? Maybe I'm treating 10 variable out of 1,000. Somebody may be using 100 variable, and he or she might be getting the good accuracy, or vice versa, right? I'm just predicting because we don't have any real-time scenario in place, right?
Yeah, so again, to answer your question, it's not person to person, but it's use case to use case. Now, if you have 5,000, 6,000 variables, you in practically won't be able to choose top 100 features directly initially without understanding the correlation between the variables, right? Now let's say you have similar category variables, you have 100 similar category variables which more or less give the same information. So there's a high chance that these variables will be highly correlated with each other, within each other, not with the target variable, but just within each other they will be highly correlated, because all of them will kind of contain the similar information. So I don't want to proceed with such kind of variables. So if I already know manually that this case is there, wherein my model has such correlated features, I'll automatically eliminate them. But when you have such a huge set of variables, it's not humanly to understand that manually, right? That's why we go with feature selection methods to understand which feature gives more importance. So let's say if you're using XGBoost, you'll get your information gain. Let's say information gain, which basically gives the understanding of which feature is contributing what to my target variable. If you're using random forest, it has a inbuilt feature selection method with us. It gives an help of which are the top features that has been used to predict the model, predict the outcome. So these are basically the methods that we are using. And just know this, it's a law. It's called curse of dimensionality, wherein any model cannot learn from huge dimensionality provided to it. Dimensionality means number of features. If you give exceedingly high number of features to your model is never going to learn from that data, because too much information will create noise, will create ambiguity to the model. And just imagine it to be a kid. If you fit the kid, if you fit the kid with a lot of data, a lot of topics to learn from in the first go, will the kid be able to learn it? Will the kid be able to grasp the concept of what he actually has to focus on?
No, actually.
No, right? Exactly. That's the same thing. You just treat your model like a kid. It's learning, it's training from your data. So you are going to use the best of the methods that are available. Simple.
Meghna?
Yeah.
Will the dimensionality reduction work in this case? Like
Yeah, definitely.
PCA?
Definitely.
Yeah.
Dimensionality.
go
There
for
are multiple
PCA.
ways to do it. Yeah. One of them is feature selection. There are multiple ways. There's PCA as well, which
Yeah.
can be used for dimensionality reduction.
So
Yeah.
do you use that in the real time, PCA one?
Many in many use cases, yes, but in many use cases, no as well. I can give an example where I had worked with, like, the one that I was just talking about, the 90 million data set and the 5,000 6,000 features that we had. We didn't use PCA because a lot of platforms don't support. So you are over here using Jupyter Notebook to build your models on. It's pretty simple, pretty easy, but that's not going to happen in a lot of scenarios, right? All the corporate companies that work have different platforms that you build your model on. Like for me, I have built that model on BigQuery. BigQuery doesn't support a lot of models. BigQuery doesn't support light GBM. BigQuery supports logistic regression, XGBoost, but it doesn't support LGBM, light gradient boosting model. So you're going to choose from what you have, and then again you choose the best that you can. So for us, we were building two models over there. One, we with all the variables possible, then a tier 2 model with only the top 50 features that actually makes sense.
Yeah, actually, we will be building models on Google Colab. In real time, anyone will build the models on Google Colab live.
I don't think so. I don't think so. You know why we can't build a model on Google Colab? So what happens? And the same happens with Jupyter Notebook as well. When there's huge data, right? Your Jupyter Notebook or your Google Colab won't be able to handle such huge data. It won't. It would either crash or fail, and that's the whole scenario of using or building data pipelines. And that's why data engineers or machine learning engineers, invest so much time in building ML pipelines or machine learning pipelines. So there are a lot of tools that you use. There's Kafka, there is Airflow, there is BigQuery. A lot of companies, like even the top tier companies like Google, Microsoft, Uber, all of these companies have their own model building platforms as well, right? So we don't always use
pipeline.
Google.
Yeah, here pipeline and everything comes under like identifying the data and doing the analysis, train and testing. This all comes under pipeline only, right?
Everything will come in the pipeline. You just set up a pipeline. It does the ETL work of extracting, loading your data set. It does the pre-processing work, how your data set should be in what form to feed the model in. Then it splits the data, it feeds the model, it fits the model, it trains the model, it does the predictions, and it shows you the result. All of it is done in pipeline. You don't sit and run the cells. That doesn't happen.
Okay.
Yeah. How to choose which method to be used based on data. Like I said, it depends on your use case and the platforms available to you. But the best way to go it is either in a feature selection method that your model, by default provides you with, like random forest or XGBoost. And the second thing is dimensionality reduction for sure. And there are a number of ways in dimensionality reduction. You should definitely read up on them. PCA is one of them, but there are more such ones. So yeah, that's again something to learn about. I hope your question is answered.
But when you have the automated pipelines, right, then still you have to write the models at least, right? Automated pipelines will obviously learn, obviously get the data, and they will be, I mean, huge databases like S3 can be used for storing the data and pulling the data from. For example, that you said Jupyter Notebook or Google Colab won't be able to assist with the large amount of data, right? And then when we are using the same models or on the same data, or we have the common data and we are doing different models, right? So it is highly
I
automated.
get your point. Yeah, I get your point. You're saying that okay, we are using ML pipelines, but someone has to understand what is the best case scenario and then set up the pipeline, right?
Yeah, someone has to understand which model to use, which
Yeah,
algorithm.
definitely. Yeah, agreed. That exercise is done. I'm talking about when we had to go build 300 400 models, right? So when we do something in such large scales and all of that has to go to production, then we use ML pipelines. But for setting up those pipelines, it's a whole different method. We get the data, we do a lot of EDA, we understand the data, we understand correlations, we spend a lot of time in doing feature engineering. So when you work with real-time data, your features won't be completely in the form that you want to. Like, let's say you're working on customer data, right? Or let's say our healthcare example itself. Now you have patient level information with us, but all of the data won't be in the best shape. All of the data won't be in the best possible size or shape. Like, let's say a person's let's say a person's high blood pressure variable right now, let's say showing as something like the higher level is 120 and the lower level is 80. We all know 120 by 80 is normal, but maybe we want to see it on a timestamp basis, that what was his blood pressure in the last 6 months, in the last 3 months, in the last 2 months, in the last 1 month. So you are going to create those features out of the data that you got. A patient's level, maybe the patient's information will be given on what was the patient's blood pressure on let's say July 2023, what was the patient's blood pressure on, let's say, December 2022. You will have multi-level data over there. You are going to create those variables and put it all into the shape to be fed into the data. So right now the data that you are using is very processed and very scalable, but in real time your data is not that much pre-processed, and that's where you get to learn, and you set up the pipelines and then you build all of it automatically. But yeah, so I think that was your question, right?
Yeah, my question is like we need the pipelines definitely, because say example 10,000 devices are there, right? And say example on each device we need to check 4 different models on each device. 4 different models are there, and say we have 40,000 models, right? And 40,000 models on the same data. I mean different data, because every device will have different
Yeah,
data, right?
yeah.
If we are training it at the same time,
Yeah.
when we are training it at the same time, then it will require different infrastructure, right? So
Yes,
it will
yes, definitely.
certain batch jobs or
Yeah,
year
yeah.
or what
Mm.
what company you are saying. So
Yeah.
it is like when we talk about practical things, then practical thing is this only, that we need the pipelines in company environment.
Yeah.
But But again, the human touch, like data engineer or ML engineer, will be needed because anyone needs to write the models, right? Anyone needs to decide which model to be used here. For
That's
example,
the work. I mean, that's the work of data scientist or data analyst, if data analyst job description includes that. But that's the job of ours to understand which model will work over here, how build a lot of models manually, test them out, see if it is working. And once everything is done, we only set up the pipelines. But the whole setup of Airflow or BigQuery or your data getting pipelined into to us, where we are just utilizing and querying and etc., that backend job is done by data engineer and ML engineer.
yeah, and that pipeline are run by ML ops or DevOps. Pipeline are taken care by ML ops.
Not always, not always. You can also do that.
Okay, so for building that pipeline, which tools we can use for building the pipeline?
You can learn about Airflow. Airflow is a good automation tool for automating a lot of such pipelines. Or you can definitely work on BigQuery. I think if you guys have attended the other project of mine that I was talking about for placement, I think I've used BigQuery for querying over there. But in real life, we use BigQuery for querying. It's super fast, the processing time and execution time is super good, and we also build models on BigQuery, so it's highly scalable product.
Actually, it is the first project class for us. Recently only completed machine learning.
Sorry?
Recently only completed machine learning last week before the only. This is our first project
Okay,
class.
okay. Got it.
So actually Airflow means like it's like Apache Airflow only you're talking about, right?
Yeah, Apache Airflow. Well, I think we went quite off topic of what we were discussing, but did you guys just get the idea that was I able to give you a practical image of how it happens in real life? Yes, do you think it was useful? Should I include such more stuff in your whole session? You think you need more such information? You can let me know. Yes, okay, great, cool. Cool, great. So, yeah, once you build your model, once you know these are the robust set of features that I'm going to build, use in my, next iteration of the model. And once we are done building that, that's when we then interpret the model results. And then there are two ways to interpret the model results. Definitely, we do cross-validation. So, how many of you guys know about cross-validation? Yes, right? So I'll just give a quick overview of what is k-fold cross-validation, where basically we divide, let's say we divide our whole data into 5 parts, like you can see over here. And in each of these 5 parts, we divide it into, let's say, 80% of training and 20% of test. So why we are doing it is because it's a better way for the model to learn. So if let's say you have just this part, let's say wherever my cursor is, this is the only data part you have. So if for every iteration, you are just training on the same 80% of the data and testing on the 20% of data. Ideally, your model is just learning from this part of the data. Maybe if you do a more, if you want your data to learn more about sorry, my bad. If you want your model to learn more about your data and the relationships between them, maybe a better approach is a k-fold cross-validation, wherein you basically divide your whole data into k parts, let's say 5 parts, and in each of these parts we divide it into their respective train and test part. So my model gets to learn from different parts of the data, and also we get to test our model on different parts of the data. So the better the more it gets to learn from different kind of relationships of the data, the better it will be at predicting it unseen data as well, right? So that's the whole point of using our k-fold cross-validation, right? So I just gave a quick overview on cross-validation, considering you all know about it, but I hope it's clear, right? I hope you guys are clear with k-fold cross-validation. Yes. Okay, I'll quickly sum up the confusion matrix as well. So this is what we call the confusion matrix, which again, I'm sure a lot of you will know. But yeah, just to give you a recap and overview, When you build a model, when you are done with the model building part and now you just want to test your model, how will you test your model? Yeah, you will basically use the predict functions to ask your model to predict on the unseen data or the testing part of the data. But how do you know the predictions are good predictions or wrong, right? You're basically, for classification itself, you're basically going to use something called a confusion matrix. So this is how a confusion matrix basically looks like, wherein here in the columns you have predicted class, in the rows you have the actual class, and very easy to remember method that I can tell you. If anyone ever gives you, I'll just annotate. Let me open up give me a moment. I'll try to open up white space. Okay, let's say someone gives you a matrix like this. Let's say your interviewer itself gives you a matrix like this and says that this is my predicted class P and this is my actual class A. This is 1, this is 0, this is 1, this is 0, right? So how do you know which is your true positive and true negative? Okay, so I'll ask from you guys, considering you guys already know about confusion matrix. So can you guys tell me what will be the first cell wherever my cursor is right now? What will be this cell known as?
True positive.
True positive.
True positive.
Okay, true positive. Cool, easy. What about this cell? The cursor is right now on?
Negative, true negative.
True negative. Okay. What about this cell?
False negative.
False negative.
False negative, right? And what about this cell?
False positive.
False positive. Great. Very easy to remember. Whenever my predictions, actual and predicted class predictions match, like 1, 1, 0, 0, my first letter will be true. Second letter will always be, what are you trying to predict? You're trying to predict a positive class. So positive, right? You have basically predicted a positive class. So positive. Same way, if you are predicted an actual class don't match, the first letter will be false. The second letter will basically be what you have predicted. You have predicted a negative class, so negative. Here you have predicted a positive class, so positive, and hence you can fill up the matrix. Easy. Everyone, I'm sure everyone is clear with here, but can you guys let me know if you guys are clear till here? Great. So our false negative is also known as what? What is a false negative also known as?
Type 2 error.
Okay. What about others?
Misclassifications.
Yeah, it is correct. Type 2.
Type 2. This is type 2 error. And likewise, your false positive will be?
Type 1.
1. Yeah, your type 1. Now I have a question for you guys. So for the use case that we have, where we are trying to predict whether a person will have diabetes or not, which error, type 1 or type 2, which error is more dangerous for us? Which is that error that you will try to reduce the most? Type 1 or type 2?
Type 1.
Type 2.
Type 1.
Type 1. Type 1.
1.
Type 1.
Okay.
Shouldn't it be type 2? Because we are actually.
Yeah, I too go with type 2.
No, we have to eliminate basically, right? So if you
reduce, you basically are trying to minimize that error.
Type 2 means because we will simply the patient who is having the diabetes saying that he don't have diabetes. So in future it may cause problem to him. Okay, maybe we predicted if some person has diabetes, maybe after some further tests he can know that he does not have. But the person who is actually having the diabetes, we are saying that the person does not have diabetes. I think false negative is somewhat error we have to eradicate.
Okay. What about others? I can see a lot of type 2s.
It's type 1.
Mm-hmm.
Type 1, I believe.
So why do you think type 1? Can you guys give me one more explanation?
Because if the patient is actually going to have diabetic, then we want to identify them.
Rather,
Yeah.
we don't want to include them basically, right? And here
Yeah.
we are trying kind of including them, so we are wasting one of the
So
slot.
if we are falsely identifying them as non-diabetic, then we have to reduce that. We want to get the people who are prone to diabetic so that we can remove them.
Okay. So in my view, it will be type 1. Why? Because let's recall back to the problem. What are we trying to do? We are trying to predict people who can be diabetic, or people who can be classified as type 1 diabetic in the near future. We want to eliminate them from the clinical trial. We don't want them to be a part of our clinical trial because that is going to cause a problem to us, right? So if my model is saying that someone is not diabetic, but in actual they are diabetic, that is a problem, right? That is a problem, because in reality that person is actually trying, that person is actually a diabetic patient and is going to catch type 1 diabetes soon, but my model is saying no, this person is not diabetic, and we include him in the trial. That is going to be a problem. So okay, did I say type 1 initially? My bad. So it's basically type 2 or your false negative which you're trying to reduce the most, right? My bad. I meant type 2, basically people who are actually diabetic, but my model is saying no, they are not. And if you include such people in your clinical trial, you are going to cause more problem, and that's why type 2 is something that we want to reduce. Clear? Is everyone clear with this concept?
Can you repeat it? Sorry.
Yeah. So your type 2 is something that you want to reduce because it's basically a false negative, wherein your model is saying that no, this person is not diabetic and he's not going to get diabetic in the near future. But in reality, he is actually going to get diabetic. So that is going to cause a problem in a clinical trial, because we want to eliminate all such people. We actually want to, our whole goal is to eliminate those people from the clinical trial. And that's the main metric or parameter that we want to reduce over here. Can I get some response if you guys are clear with this concept? Great, great.
Yep.
Great. Now let's say if there would have been a scenario where both, let's say, okay, first let's say we discuss, let me just delete all the drawings, close the annotations. Okay, coming back to our confusion matrix. Okay, we all know about precision, we all know about recall, sensitivity, accuracy, etc., etc. We know the formulas, we know all of it, right? We know what is precision, we know what is recall over here. Now let's say in a scenario where both precision and recall is equally important to us, what is the metric that we will be going ahead with? Okay, I get an answer of recall. What about others? Then Lakshmi says F1 score. What about others? Shruti says recall. Question, please. I'm saying that you have your precision over here, which is basically your true positive divided by true positive plus false positive. And you have your sensitivity or your recall over here, which is basically your true positive divided by true positive plus false negative, right? You either focus on precision or you either focus on recall usually, right? Let's say we are solving a business case where both precision and recall are equally important to us. What metric will be using in that case? I get a lot of answers with recall, but any more answers before I just spill out the answer?
So you're giving us the option for only precision and recall, right?
Yes, yes,
Yeah.
yes.
So we don't want to miss any positive cases, so we will increase recall and reduce precision, I should say.
Okay, I'll just give my part of the answer. I was intending to know a metric which harmonizes both of them, which is F1 score, which is a harmonic mean of your precision and recall, and it balances both your precision and recall. So in cases where both precision and recall are equally important to us, we'll go with a metric called precision recall. So people who answered F1 score, good job, guys. Okay, that was the answer that I was looking for. So are you guys clear why I said F1 score? Yes? Can I get some more response? Come on, guys. Yes. Great. Okay, Vishal says no. Okay, I'll just repeat. I was just looking for a metric. It is not related to the problem that we are solving. I was just looking to know that if you guys are understanding that in business cases or in use cases where both precision and recall is important to us, and if we want a unified metric which balances both precision and recall, which is the metric that we will be going for? That is basically F1 score, which is basically your harmonic mean of precision and recall, and it balances the importance of both precision and recall in our case, and that's why F1 score is the right answer. Clear? Okay, great. Now I'll just stop sharing my screen and just give you guys a glance of the data set, since we are kind of high on time today. But yeah, just give me a moment.
In the meantime, why type 2 is more uh, dangerous, or why type 2 is more error prone than type 1?
You want me to answer that? Why did I choose type 2 as to prioritize type 2, right? Yeah. So that's because your type 2, what is your type 2 saying? Your type 2 is basically saying that your model has predicted to the patient as non-diabetic, that the patient cannot have type 1 diabetes in the near future. But in reality, that person will be having type 1 diabetes in the real future, right? And in our clinical trial, I want to eliminate all such people who can have my whole point of doing this exercise is to eliminate people who can have type 1 diabetes in the near future. And my type 2 error is basically saying that these are the number of cases where my model has said that no, this person is not diabetic, but in reality the person was diabetic, so it was a false prediction, and that is something that I want to reduce, and that's why type 2 error. Clear?
Type 1 also takes out healthy individuals, right? Saying that they are type 1 diabetic. So in both cases, we
Yeah,
are getting
both
the
are obviously misclassifications, or both are equal. I mean, both are harmful to us. But if you still have to prioritize one, you would rather go on with the negative one. Imagine taking more of people who are actually going to be diabetic in the future, and we just taking them onboarded with us. So that is going to cost us more money. That is going to rupture our whole clinical trial more, right? That's why type 2 error.
Yeah, our objective is like that, to identify in the future whether these people are getting type 1 diabetes or not only, right?
Yes. And eliminate them from the clinical trial. Why are we trying to identify if they will get type 1 diabetes or not? To eliminate them from the clinical trial, right?
Sure. Okay.
Yeah,
but
we don't want such people.
who are
Yeah.
not going to have type 1 diabetes, and we have to eliminate from the clinical trial. This is our objective.
Yes. Clear?
Can
Is
we get
everyone clear? Yeah, sorry. Please go ahead.
Can we get this file?
You want me to repeat?
This file, the file you're uploading.
Yeah, I'll give you the file, no worries. Okay, I'll just repeat once more. Type 2 error is something that we will focus more on in reducing, because type 2 error we will be giving us the cases wherein my model has misclassified my diabetic patients, saying that these patients don't have diabetics or will not have diabetics in the near future, but those are the patients who will actually be having diabetes in the near future. So I don't want that case to happen, because I want my clinical trial to be with patients who will not have type 1 diabetics in the near future, right? I want to eliminate those people who will who will catch type 1 diabetes soon. So I don't want to short people who will anyway who are anyway very prone to diabetic, and who will anyway get diabetes in the near future. I don't want such people, because then the drug testing will not be of any use to them, right? That's why type 2 diabetes. I'll just quickly show you guys a glimpse of the data over here, and then we will continue with the EDA and etc. in the next class, because we are high on time. But yeah, I've just imported all the libraries, and I've imported my data set. That's how my data set looks over here. you have different columns, but your outcome column becomes your target variable over here, where which basically says that 1 means that person has type 1 diabetes, and 0 means that person doesn't have type 1 diabetes. You have your age, you have your, okay, my bad, you have your age, you have your diabetes pedigree function, you have BMI, insulin, skin thickness, blood pressure, glucose, etc, etc, right? And like we can see from here, just give me a moment. Yeah, like we can see over here, we have 768 such patients. Like I said, this is a sampled data set of what we are using, and that's why 768 patients on whom we will be training and learning our model from. So what I'll do is upload this data set to you guys. Since you guys know all of you guys know Python, right?
Yes,
Yeah.
Yeah, so I'll be uploading this data set for you guys. I want you guys to do a basic EDA on it. I want you to use your brain and your analytical skills over here. Do a basic EDA on it, and next class when we start, you guys can help me with the insights. You guys can help me with better hypothesis forming, and this way you will be better exploring the data on yourself rather than me showing you this is how the data looks like. I gave you an introduction to the data. I'll be uploading the data. You guys know Python, and I want you to use your analytical skills and explore the data more. So can I expect that from you guys?
Yeah, sure.
Sure.
Hypothesis means like you're doing like hypothesis testing, right?
You don't have to do hypothesis testing completely. You just have to explore the data. Just pure explore the data.
Okay.
Meghna?
What's the
Sorry?
Meghna?
What's EDA, please?
It is exploratory data analysis, where you just explore the data. You just know about the data more, understand the data more. Right? I want to use, before I give out a detailed explanation of what you can do, this, that, I want you to use your analytical skills and understand the data first, and then we'll discuss.
Oh, sure.
Meghna, can you share the drive link?
Yeah, I'll do.
Hmm.
I think the drive link is same. I'll just ask the team to convey to you guys.
Yeah.
Because the present drive link is like of machine learning and like where the project drive link will upload, we also do. Yeah, that's it.
I'll ask the team to convey to you guys for sure. Cool. So we come towards the end of our session. So I'll just take some time and understand that. Did you guys understand the session today? Did you guys understand? Did you guys understood all the details that we discussed today? Yes? Did you find something new? Did you learn something new and interesting? Yes? Okay. Great. Thank you so much for attending the session. So before closing the session, I just want to know if you guys have any doubt or anything. I'll just take a minute or two to answer your doubts as well.
How many more classes are required, Meghna,
I think the next
to
class will
complete
be
this
enough.
one?
I think the next class will be enough. Yeah.
Yeah.
No, the one which confusion matrix which you talk about, type 1, type 2, right? So it is better, like I gone through it and I understand it in terms of misclassification and correct classification. And based on that, I used to draw the conclusion. That is also correct, right?
Yeah.
Because hopping to one one concept to another, though the concept is same, but something is getting into
Concept.
head, so it makes some confusion. It is all
Yeah.
right, right?
Yeah, it is all right. The concept is actually same. It's just the way of understanding.
Yeah.
But at the end of the day, you are just learning the similar thing. You're just getting your basics clear.
Correct.
Yeah, if we are enough confident to explain it, can we add this project in our resume?
For sure, yes. You're just getting one more domain to add, right? Healthcare is something which is always in demand. So you can obviously speak that you have worked on a healthcare domain problem statement.
Okay. So this okay. In the next session, from starting from the scratch, yeah. While developing the code and everything, so everything will be from scratch only, right?
Yeah. Provided that all of you guys put your hands on the data and get your hands dirty on the data.
We will do our part also.
Yeah. Great.
Yeah, thank you.
Cool. No more doubts? Nothing?
Are you also going to cover any projects related with the security or something like that, specific to cyber
Are
security?
you talking about risk assessment?
Domain. I'm talking about the domain. Currently, you are talking in terms of healthcare domain, right? So I was talking, whether you are also going to perform any, this sort of, project related with the network security or cyber security?
I'm not sure about that, but we can definitely discuss and let you guys know. Cool. Any more doubts? Any more discussions?
Yes, Meghna, I have a doubt
Hmm.
regarding we will take the entire data set as train and cross-validation set, right?
Yeah.
So we have a separate test. Other than this train and cross-validation, we have another test set, right? I have seen some classes saying we will divide the data into 3 parts, and one part will take for test set also. So, do we have some more information about that set? The test set.
It's just a way of doing it, right? You can
Okay.
either, let's say you have 100 rows. Okay. You can either use 80 of them to train your model on, and you can test how your model got trained on the rest 20 of them. That's one way to do it. The other way to do it is, let's say you train your model on 60 of the rows. Okay, let's say you train your model on 60 of the rows, and you test it on for the next 40 rows that you have. You again divide it into 20 and 20, and then you test your model on the first 20 set of the data. Whatever results you get, you improvise your model more on it, and then test your model on the other 20 set of the data and get a more robust performance. That's again one way of doing it. Cross validation is basically your 100 rows that you have. Let's say you divide it into 5 parts, so 20 rows each. Right, and in each of those 20 rows, let's say you are using 15 rows to train, 5 rows to test in each of those groups. So it's different way of doing the training and testing, just for your model to understand the data better, just for your model to understand the relationship better. Now, definitely cross validation works better when you have more number of rows, more number of data, more data points to yourself. But when you have comparatively lesser, like in our case, cross validation won't be of utmost importance. Yeah.
Okay. So we'll use test set rather than the cross validation set.
Yeah, we'll mostly be dividing it into train and test split, and then
Okay.
we can use it likewise. Yeah.
So in real world, we will be using cross validation set also. In all the cases.
Sometimes yes, sometimes no. It depends on the use case again.
Okay. Fine.
Yeah. So I have a question: on what basis we decide to opt for both accuracy and recall? Accuracy and recall is again different things. Okay. Accuracy is like you're seeing how accurate your predictions are, whether it is the prediction of whether the person is diabetic or non-diabetic, be it 1 or 0, you are seeing overall what was the accuracy of my model. Recall, on the other hand, you're saying that how many predictions were correct about the diabetic patients only. How many predictions were correct just to focus on the diabetic patients, just that. So there's nothing about both accuracy and recall. We either choose between precision recall, or we harmonize both precision and recall. And accuracy is something different. Accuracy is like checking overall performance of the model. I
So
hope that's
why
yeah.
we are trying to trade off between precision and recall in our scenario?
Yeah.
Because here
No,
we are
we're
giving.
not trading off right now. I'm just giving an example.
Right now we are giving more importance to recall only, right?
Right now we are recall. Okay, before that, precision is basically your TP divided by TP plus FP.
Yeah.
Right?
Yes.
Your TP and FP is predicted positive class. So what is your model trying to say? Out of the predicted positive class, how many were actually correct predictions about the positive class?
Yes.
Right? Your recall is saying what? Your recall is TP divided by TP plus FN. So your denominator is TP and FN. So that's the actual positive class, which basically gives a better overview, right? Out of all the actually diabetic patients, or out of the actually positive patients that we have, how many were correctly predicted as diabetic patients? So that is of more importance to me, right? Out of all the people that I have in reality, in actual class, not the predicted ones, how many were correct predictions? So that is of more importance to me. So in my case, definitely a recall makes more sense.
Okay.
Right?
Okay, yeah.
Cool. So is everyone clear with the class?
Yes, yeah.
Great. Thank you so much for attending the session, guys. Lovely hosting all of you. I'll see you guys in the next session. Okay, thank you. Good night.